Section P7 is a fun section to look at. It really involves a bunch of different things. It's going to be talking about solving equations, and the equations that we're going to be solving in this section, it really puts a lot all into one section because we'll look at linear, which is kind of boring, but then we'll also look at quadratic, rational, and radical equations too. Particularly those last two, the rational equations and the radical equations, students typically have some trouble with. Okay, so let's go ahead and get into our section here. I will share my screen with you. And for this section with equations, we'll start off just talking about all the content that we'll be discussing in this section. And like I said, it's a lot. So we'll first solve linear equations in one variable. You've been doing that since Algebra 1, pretty straightforward. We'll make sure your skills are good with that. And then we solve linear equations containing fractions. That makes it a little bit more interesting. And then we'll solve rational equations with variables in the denominator. Remember, those rational equations, anytime you have variables in the denominator, you're going to have values that are restricted. So if you get a solution for x, you'll have to make sure it's not one of the restricted values, because if it is, we would have to say that there is no solution. Solve a formula for a variable. So maybe there's more than one variable in the problem, and I'm asking you to solve for a specific one. Solve equations involving absolute values. So even absolute value equations, they're pretty straightforward. Quadratic equations by factoring. And then we'll also use quadratic equations by the square root property, quadratic equations by completing the square, and then quadratic equations using the quadratic formula. My guess is most of you have been in classes which really stressed solving quadratic equations by using the quadratic formula. If so, that's kind of unfortunate. I will de-emphasize the quadratic formula in this class because it doesn't really help that much going forward. The quadratic formula, you're really not doing algebra when you do it. You're just doing arithmetic. So solving by completing the square will be much more useful in future classes. Use the discriminant to determine the number and type of solutions in the quadratic equation. So the discriminant is the b squared minus 4ac part of the quadratic formula. It is a handy tool, especially to make sure that you don't go through a problem trying to look for a real solution all that while just to find out there are no real solutions. And you could have found that out much more quickly using the discriminant. So we'll talk about that. Determine the most efficient method to use when solving a quadratic equation. And if it's big numbers, that most efficient method will be the quadratic formula. But if it's just standard numbers, I would hope it's one of the other methods. And then solving radical equations. So first of all, our linear equations, you know, y equals mx plus b. Well, this is the same idea. We say a is the coefficient of x, ax plus b is equal to 0. And we know that this is a linear equation as long as the coefficient of that x term isn't 0, because then, of course, it's just a constant. Now, if we're trying to solve a linear equation, you can simplify the algebraic expression on each side by removing grouping symbols and combining the like terms. We'll collect all of the variable terms on one side, and any numbers on the other side. You can isolate the variable and solve at that point, and you can check your answer. Now, I will have the answer checks for linear equations, quadratic equations, absolute value. I'll do it for every single one of these. In reality, I don't go in and check my answer all of the time. And I don't necessarily expect you to either. You can if you want. You always can check your answers. So I do on these slides, but you don't necessarily have to. Now, the times when we will have to, the last topic in this section, I look at radical equations. You have no option to check your answers there. You have to. And we'll talk about that when we get to it. First up, solving a linear equation. Let's say I give you the linear equation 4 times the group 2x plus 1 equals 29 plus 3 times the group 2x minus 5. Well, if you go back to my directions, the first thing I said is to get rid of any parentheses on each side. So when I'm trying to solve this linear equation, that's the first thing I do. I'll distribute the 4x through this group and I'll get 8x plus 4. On the right-hand side, when I distribute the 3, I'll get 6x minus 15. Now, at that point, I'm in much better shape, but I'll go ahead and combine any like terms on the side, and you could combine multiple steps in one. I'm showing each and every individual step. If I combine the constants on the right, I'll get 6x, and then 29 minus 15 is going to give me plus 14. So now I get it down to a much simpler expression. The 8x plus 4 equals 6x plus 14. I want to collect the variables on one side and the constants on the other side. So in this case, I'm moving the variables to the left-hand side. And when I do that, 8x minus 6x just gives me 2x plus 4 equals 14. You could have went ahead in this same step and moved the constants to the right. I chose to do that in another step to make sure you see every single step here. If I subtract 4 on each side, well, 14 minus 4 is 10. Once you get the variables on one side, the constants on the other, now it's an easy process. You can just say, well, if 2 times x is equal to 10, I can divide by 2 on each side and get x is equal to 10 over 2, or x is equal to 5. Now, I know that that's my solution for x, or at least I think it is. And as long as you haven't made any mistake, that is the solution. Linear equations always give you the correct solutions if correct algebra is used. That's not always the case in other types of equations. But in this case, just to make sure we didn't make any errors, you could plug the 5 back into the original problem. And when you did that, here's your original problem. 4 times the group 2x plus 1 equals 29 plus 3 times the group 2x minus 5. Please notice I'm just plugging a 5 wherever there's an x, a 5 wherever there's an x here. On the left-hand side, this group would become 2 times 5 plus 1, that's 11. I'll have 4 times 11 is 44. So my number is a 44 on the left-hand side. This is only a true statement if I have a 44 on the right. Well, please notice, when I plug a 5 into the right-hand side, I have 2 times 5 minus 5. That's 10 minus 5 is 5. So now on the right-hand side, I have 3 times 5 is 15. 15 plus the preceding number 29 also gives me 44. So yes, I get both sides are equal to 44 if x is equal to 5. And that was our whole point. We wanted to find the value of x to which the left-hand side of this equation was equal to the right. That's true. And now, please don't make the mistake in thinking 44 is your solution. 44 is the dependent variable when the independent variable x equals 5 is the solution set. So we can say x equals 5, solution. Now again, this last step, step 4, I'll never ask to see it. You can do it if you want, but it's not required. Whoops, I went 2 slides. Up next, linear equations in which we have fractions involved. Now, this is not a rational expression because there's no variables in the denominator. The first thing I would do if I were looking at a problem like this, and you could just go ahead and attack it directly and say, well, your left-hand side is 1/4 minus 3/4 is equal to 5/14 minus 1/7 x plus 5, or sorry, minus 5 over 7, because that negative would distribute to both terms in this last group. That would be okay, but I just think it's easier, and I think a lot of students think it's easier if you get rid of the fractions first before trying to work the problem. You can get rid of any fractions inside of an equation if you multiply both sides by the least common denominator. So when I look at this, I can say, well, I know the denominator has to at least have a factor of 4. And then this would say 14. Well, 14 is 2 times 7. And I say, well, does it already have a factor of 2? Yeah, 4 has a factor of 2. So I only need the additional factor of 7. I can say, well, 4 times 7 is going to be 28. All 3 of those denominators are factors of 28. So I can say my least common denominator is 28. So now I take that 28, I distribute it to every term throughout the entire problem, or on both sides of the equation. When I do that, This 4 on the left cancels with the 28. I just have 7 times that group x minus 3. On the right, 14 goes into 28 2 times. I'll be left with 2 times 5. And 7 goes into 28 4 times. I'll have minus 4 times the group x plus 5. At that point, it's really easy to distribute. I'll have 7x minus 21 is equal to 10 minus 4x, and then please make sure you see where this minus 20 came from. That negative 4 had to distribute to both terms inside that binomial expression. So minus 4x minus 4 times 5, that gives me minus 20. Now, all I'm doing is I'm combining the constants on the right. I'll have negative 4x plus 10 minus 20. That gives me negative 4x minus 10. Then I can say, well, if I wanted to gather the x on the same side, I would add 4x to both sides. And notice I didn't show the plus 4x plus 4x. I'd rather you not. You can just go to this without showing that. You can put the plus 4x on each side if you like, but it's better not to. So now I have 11x minus 21 equals negative 10. I add 21 to both sides. Negative 10 plus 21 is 11. Now we get 11x is equal to 11. We can divide by 11. We get our final solution of 1. Now you can say, well, okay, the final step here is you could check it. And again, I'm not big on this checking. You can if you want, but you certainly don't have to. If you plug a 1 into the original left-hand side, you'd get 1 minus 3 over 4. That becomes negative 2 over 4. And I know negative 2 over 4 reduces down to negative 1/2. On the right-hand side, if I try to plug in the 1, there's nowhere to plug it in this term. It's just a 5 over 14. But then I'll have minus 1 plus 5 over 7. That's going to be 1 plus 5 over 7 here. I'm getting 5 over 14 minus 6 over 7. And this question mark is because all I'm trying to do is determine, does this side equal this side? So I'm saying I don't know if this is true until I get to the very end. So if this is true, then my solution is valid. If it's not true, then my solution is invalid. I get 5/14 minus 6/7 on the right-hand side. I already know my left-hand side reduced down to negative 1/2. 5 over 14 minus 6 over 7 has a common denominator of 14. I would multiply the second fraction by 2 over 2. That's going to give me minus 12 over 14. 5 over 14 minus 12 over 14 gives me negative 7 over 14. We know negative 7 over 14 is negative 1/2. So then we can say, well, yeah, of course. Negative 1/2 is equal to negative 1/2. Every single solitary time your solution is true, you're going to get a similar scenario to this, to where the left and right-hand side have the exact same number. So yes, we can say our solution set is 1, or I would just put x equals 1. Now, solving rational equations, please don't mistake the problem that we last did with a rational equation. Rational equations, yes, they have fractions, but they have fractions in which the denominators are not simply constants. So the last equation that we just worked together, that was just a linear equation that involved fractions. However, if I want to work a rational equation, and oh, I do, then all I would do is stick variables in the denominator. That makes it for a lot more fun. Let's look at that problem. If I ask you to solve a rational equation, first thing I would go ahead and do is just factor all of your denominators. Now, a tip for practicality, if you have 2 linear factors on one side and a quadratic factor on the other side, I will bet you 99.5% of the time, the quadratic that you have on the right-hand side will just factor to be these 2. So you don't have to even put a whole lot of thought into the factoring in a problem like this. If you use some common sense, it's pretty much done for you. So I can say, ooh, I bet that quadratic factor x squared plus x minus 6 factors to be x plus 3x minus 2, doesn't it? Yes, because 3 times negative 2 is negative 6, and 3 plus a negative 2 would add to give me the positive 1 in the middle. So I can see that that quadratic factor denominator has the same denominator as the other 2. Now, instantly, I can see, well, then the only 2 factors I have throughout my denominator in the entire problem are x plus 3 and x minus 2. If I set each of those factors equal to 0, This is telling me that, well, okay, then I know that x cannot equal -3, because if it does, this factor would equal 0, which would make this fraction not exist. What about if x equals 2? Well, it can't, because if it did, this fraction would be undefined. 5 over 0 is undefined. So I need to remember, if I get a solution of -3 or 0, I would have to eliminate it and say that's just an extraneous value. It cannot be a solution. Now, my least common denominator, I've already talked about that. It's both of those factors, x plus 3, x minus 2. I'm going to multiply that least common denominator just like I multiplied the 28 in the last problem. I'm going to multiply this problem by x plus 3, x minus 2 throughout to clear the fraction and throughout the entire problem. Now, what I've seen some people do in this problem is, or in problems like this, is they'll think, ooh, all I have to do is get a common denominator throughout the problem, and they'll keep the fractions in the problem. That is an inefficient way to work these problems. Anytime you see fractions within an equation, your goal should be to get rid of them. So I'm seeing these fractions and think, well, how can I get rid of them all? I'll multiply every single solitary term by x plus 3 and x minus 2. Now, when I do that, this 6 over x plus 3, well, I know the x plus 3 cancels out, but I'm going to have 6 times x minus 2 left over. The next fraction, minus 5, the x minus 2 cancels out, but I'll have minus 5 times the other factor of x plus 3. And I know on the right-hand side, that entire denominator cancels because it's the same thing as the least common denominator of x plus 3, x minus 2. So the right-hand side just becomes -20. Now I have a pretty nice linear equation, which I can see if I distribute on the left-hand side. I'll have 6x minus 12, and then minus 5x minus 15. Once I collect like terms on the left-hand side, 6x minus 5x is just x. -12 minus 15 is -27. So now I have x minus 27 is -20. Well, I'll add 27 to both sides to solve for x. X is going to equal -20 plus 27. When I do that, I get x equals 7. Now, I know that x equals 7, that's not one of the restricted values. So I'm certain, yeah, that's a solution. I'm confident I've done the problem correct. But just to make sure, I went ahead and checked it again. So if you want to, you can always check the proposed solution. So I can say, well, I'm sure the answer is 7. Well, okay, prove it. Well, I plug a 7 in for x. In that first fraction, that's going to give me 6 over 7 plus 3. The second fraction, I'll have 5 over 7 minus 2. And then over here, I'll have -20 over 7 squared plus 7 minus 6. On the left-hand side, I'll have 6 over 10 minus 5 over 5. That's going to be easy to work with. The right-hand side, I know 7 squared is just 49. I'll have 49 plus 7 minus 6. That's going to be 49 plus 1. It's going to be a 50. So my right-hand side is going to be -20 over 50. The left-hand side, I could get a common denominator. Well, actually, I can reduce down the 6 over 10 to 3 over 5 and say 3 over 5 minus 5 over 5 is going to give me -2 over 5. The right-hand side, -20 over 50, also reduces down to -2 over 5, and I can say, just like was supposed to happen, whenever we plug in a 7, the left-hand side is equal to the right. That is evidence that our solution was the correct solution. Now, solving a formula for a variable means rewriting the formula so that the variable is isolated on one side of the equation. I see students really struggle with these sometimes. Look at this glorious problem. So you say, well, it's really nice since we just talked about a rational equation. You said, well, this is just a rational equation. It's just now, instead of only being in terms of x, it's in terms of p, q, and f. Gorgeous. Now, I'm asking you to solve this formula in terms of q here. So we said, well, all right, if I'm trying to solve that in terms of q, what should be your first step? The exact same first step you did in the last problem. What was the first step we did? You found the least common denominator, and then you multiplied that denominator on both sides of the equation. Same thing here. When you find the least common denominator of this, you'd say, well, clearly it's just P times Q times F. So I'm going to take a P times Q times F, multiply it by every single term throughout that equation, and that will give me an equation without any fractions, much easier to work with. When you multiply the 1 over P by PQF, you'll just get QF. When you multiply the 1 over Q by PQF, of course, you'll get PF. Poof. On the right-hand side, you're dividing by F, multiplying by F, that'll leave you PQ. So now, making sure you go back to the problem's goal, we were supposed to solve for Q. Well, think about this and say, well, how can I solve for Q in this expression? I only have one term that has a Q. It's, two terms, this term QF and this term PQ. So I would say, well, all right, if I'm ever going to solve for Q, I need to get every term that has a Q on the same side. So from this step to the next, I just said, let's subtract QF on both sides. When I do that, it's going to cancel on the left, and I'll just have PF is equal to PQ minus QF. Then you can say, now that you have the terms of Q on the same side, why not go ahead and factor it out? I can factor out a greatest common factor of Q on the right-hand side, and when I do, I'm going to have Q times the group P minus F. Nice. So then I can say, well, if Q times the group P minus F is equal to PF, then Q is equal to PF divided by what was previously multiplying it, the group P minus F. And you don't need a parentheses down there since the denominator assumes an automatic parentheses. You don't have to put it. You could, but you don't have to. Now, like I said there, that's a gloriously fun problem. Love that one. Make sure you look at the formulas in the homework. Those are problems that I really want you to focus on and make sure you're comfortable with. Now, equations using absolute value. Whenever we think of absolute value, I just need you to remember, anytime you're saying the absolute value of any number is equal to a term, and it's always going to be a positive value, since an absolute value can only equal a positive. But what that means is that the number on the inside of the absolute value, it could be that number, and then the absolute value is doing nothing. Or it could be the negative of that number, and then the absolute value is changing the sign. So when we say the absolute value of U is equal to C, that is literally saying, well, U could equal C, or U could equal the negative of C. And we have to remember that for our equations, such as right here. If I give you 4 times the absolute value of 1 minus 2x minus 20, and I say, guys, that's equal to 0. I need you to solve for x. Your goal should be, well, let's get the absolute value all by itself first. So I can say, well, all right, if my goal is to get that by itself, what's the first step that I do? Add 20 to both sides. So then I have 4 times the absolute value of 1 minus 2x is equal to a positive 20. Now, what I do from this step to the next is I need to get that absolute value by itself. Right now, it's multiplied by 4. So I just divide by 4 on both sides, and I'll get the absolute value of 1 minus 2x is equal to 5. Now, at this point, you need to understand this means 2 different things. It could mean what's inside the absolute value could literally equal 5, and if so, the absolute value doesn't do anything. So you have the 1 minus 2x could equal positive 5, or what's inside that absolute value could be the negative of the other side, and in that case, the absolute value would change that negative 5 to be a positive 5 and still give you a solution. So I can say, well, 1 minus 2x could be 5, or 1 minus 2x could be negative 5. Now we solve out both of those pretty simple linear equations, and I'll say, well, in this first one, I'll subtract 1 on each side to get negative 2x is equal to 4. Then I divide by negative 2. 4 divided by negative 2 is negative 2. One solution should be x equals negative 2. My other solution, when I set this equation equal to a negative 5, I subtract 1 first and get negative 2x is equal to negative 6. We divide by negative 2. Negative 6 divided by negative 2 is positive 3. So right now I'm thinking, okay, the solution for x are both -2 and 3, and I'm confident that those are the solutions. Oh, and I didn't show that in this case. You could check both of these back into the original equation. You never have to check though, except when you work with radical equations. Absolute value equations, any answer you get should be the answer unless you've made some algebra error. Definition of quadratic equations. So quadratic equation is just whenever you have the highest power of x being to the second power, and you'll see the general form is ax to the second plus bx plus c is equal to 0, where a, b, and c are real numbers. They can't equal 0, of course, because then that would mean that that term of the variable is not there. Or a cannot equal 0 at least, because then it would just be a linear equation. A quadratic equation in terms of x is a second-degree polynomial. Now, whenever we're solving these out, especially if you're solving it by factoring, you're going to need to remember the zero product property. And that zero product property principle is just saying that if you have terms multiplying, if I say, hey guys, this number a times this number b is 0, well then what you note, the only way the product of two numbers can be 0 is if either the first number is equal to 0, because 0 times any number is 0, so a could be 0 or b could be 0. So I can say, well, what if a is 7? Well, as long as b is 0, 7 times 0 is still 0. So either one of them could be 0, or it could be both. So this is the inclusive or. The first one could be 0, or the second one could be 0, or yeah, they both could be 0, since 0 times 0 is also 0. Now, solving a quadratic equation by factoring, we will get all of the terms on one side and a 0 on the right-hand side. That'll be the first step. And then we're going to factor the non-zero side. And then once you get that factored, we're going to use that zero product principle that we discussed on the previous page and say, well, if this group times this group is equal to 0, either the first group or the second group must equal 0. And then you'll solve those equations from setting each factor equal to 0, and then you can check your solutions. We don't have to check the solutions here, but you can. Now, for example here, if I say solve by factoring 2x squared plus x is equal to 1. First step, move any terms over to one side to force a 0, in this case, on the right-hand side. And then once you do that, this one's pretty easy to factor, because you'd say, I know that the only two numbers that can possibly multiply to get a 2x to the second are a 2x and an x. So 2x times x is going to give me x to the second. And then the only numbers that can multiply to give me a -1 are a -1 and a +1. Now, since my middle term is positive, I had to make sure the +1 is opposite the 2x. That way, when I FOIL it out, it'll be plus 2x minus 1x for that plus 1x in the middle. Now, so I know that this is correctly factored using the trial and error approach. Once it's factored, you set each of these factors equal to 0. So 2x minus 1 is 0, x plus 1 is 0. This will give you 2x is equal to 1, and x is 1/2. Over here, you just get x equals -1. Now, I'm confident both of those are solutions, but if you wanted to check, all you'd have to do is plug it back into the original equation. You can say, well, if I'm trying to check 1/2, I'll have 2 times 1/2 quantity squared plus 1/2. That better equal 1. Well, 1/2 squared is 1/4. 2 times 1/4 is 1/2. I'll get 1/2 plus 1/2 is 1. That's a valid statement. 1 is 1. So I know 1/2 has to be a solution. On my other one, x equals -1. I'll have 2 times -1 squared plus -1 is equal to 1. Well, I know -1 squared is just a 1. And I'll have 2 times 1 is 2. 2 minus 1 is 1. And that's certainly equal to 1. So 1 is 1. Check. So whether we put a 1/2 or a -1 into our solution, or sorry, into our original problem, each of them give us a true statement. So both of these our solutions. Now, the solving quadratic equations by the square root property. Anytime you have a group squared, it really makes it ideal to go ahead and solve by the square root property. Something I need to remind you of here is that if you have u squared equals to d, please remember u could be a positive or a negative number, because if u were a negative number, u squared is going to be a positive number. So that's why I say whenever we have u squared is equal to d, we're going to have exactly two solutions. U could be the positive square root of d, and u could be the negative square root of d. And again, that's because if you plug that back into the original, the negative square root of d quantity squared is just going to be d. So both of these are correct statements. Now, to write it all as one succinct answer, you could just say, well, how about I just say u is equal to the positive negative square root of d? See, that would be good. Up next, if I'm trying to use that square root property, let's look at this equation. Now, in the square root property, you're always going to be trying to get the squared term or the squared group by itself. In this case, I don't have a squared group, but I have the squared term, that x squared term. So since I don't have a term of x, now if I had had an x squared term and an x term, you'd have to use some other technique. You'd have to use completing the square, factoring, or quadratic formula. The square root property is only going to work when you don't have a variable raised to the first power. So I can say, well, I have a variable raised to the second power. Let's get it by itself. I get it by itself by moving a 21 to the right-hand side. Then I'm going to divide by 3 on both sides, and I get x squared is equal to 7. Okay, now the principle of square roots just says, we'll take the square root of both sides, and remember, the side not containing the squared term has to be the positive or negative square root. So x is equal to both the positive and negative square root of 7. I actually prefer the answer just in that format. If you write it out in set notation, you could say it's the set of values negative root of 7 and the positive root of 7. I actually just prefer this right here, though. Now, related with that is the completing the square technique. And the completing the square is saying, well, okay, what if you have an x squared term and an x term, but you want to be able to create a group squared in order to use that principle of square roots. And this is actually an extremely important technique, and it's a technique that unfortunately a lot of students don't do in their Algebra 1 and Algebra 2 or maybe even high school pre-calculus classes. This technique is absolutely mandatory in Calculus 2 to rewrite the denominator as a perfect square trinomial in order to be able to integrate it. So this is an extremely important technique if you haven't seen it before. So let's say I just had an x squared plus a bx term, but I'm trying to create a perfect square trinomial. There's no question what the constant is. Every single solitary time, that constant needs to be half of whatever the coefficient of x is, quantity squared. So let's say, for example, the coefficient of x was 6. Then you say, well, 6 over 2 is 3. 3 squared is 9. I would need a plus 9 to make this a perfect square trinomial. Now, what that is always going to factor to is going to be x, and you keep whatever this sign. If it's a plus, you keep a plus here. If it's a minus, you keep a minus here. But in this case, it'd be x plus b over 2 quantity squared. That would work backwards to give me this group. Now, how that helps me work equations is such as the following. If I ask you to solve by completing the square, first of all, I look at the left-hand side and I say, well, if I could factor that left-hand side, I should go ahead and do it. But you can't. You can't find factors of -1 that sum to get to 4. It's not going to work. So what that tells me is that that -1 is not helpful there. I'm going to go ahead and move it to the right-hand side. Now I'm looking at the left-hand side and say, it would be nice if I could create a perfect square trinomial there, and that's what I'm going to do. So please notice, as long as I add the same term to each side, it's a legal algebraic maneuver. So what I'm choosing to do here is I can say I can create a perfect square trinomial by adding half of b squared. Well, half of 4 is 2. 2 squared is 4. I'm going to add a 4 to both sides. I left it looking like this so you can see where that came from. Now on the right-hand side, the 1 plus this group that's equal to 4, that's just going to give me a 5. On the left, the whole point for creating that perfect square trinomial is so that you can write it as the group x plus 2 quantity squared. Now, if there's any doubt, you can FOIL it out. A lot of students say, well, I don't know where you're getting this from. It's the formula. It's always x plus whatever half of this number is, quantity squared. But please notice, if you said x plus 2 times x plus 2, you would get x squared plus 2x for plus 4x. And then plus 2 times 2, that's going to give you plus 4, which is what that right there is. So you can say, okay, yes, this does represent that. It's a more efficient and effective way to write it because now all I have to do is use the principles of square roots on both sides. Square root of the left-hand side gives me x plus 2. I have to take the positive and negative square root of the right-hand side. So now I get x plus 2 is equal to the positive negative root of 5. Subtract 2 on both sides, we'll get x equals negative 2 plus or minus root of 5. Gorgeous problem. Gorgeous. Please, please, please make sure you take a look at the completing the square problems. There's at least 3 or 4 in the homework. There's not as many as I would like to see in the homework, but there's 3 or 4 of them in there that are good problems. Now, my least favorite form of solving quadratic equations is the quadratic formula. Now, for high values of a, b, and c, like if a, b, and c are in the thousands, or if they're involved like a lot of decimals and stuff, absolutely, this is the most efficient way. But if a, b, and c are just like numbers 1 through 9, I almost find it offensive to depend upon the quadratic formula. This is not algebra, so please do not think, ooh, I'm doing algebra. You're not. You're doing arithmetic if you use the quadratic formula. You're just plugging numbers into a formula already predetermined and just working out the numbers. Okay, but well, let's make sure we can do that. So as you've probably seen many times, hopefully many times before, the quadratic formula is the x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. And I intentionally do it to pop goes the weasel just because it's a childish mathematical technique and I'd really rather you get out of using it. But again, it's a good crutch technique for when we have a difficult problem to work with. Now, to be honest, this problem, I would never use the quadratic formula on it. It's too fun to work with other techniques, such as completing the square or factoring. But we'll go ahead and show the quadratic formula and how it works in this one. So you have to remember that a is always the coefficient of the x squared term, b is the coefficient of the x term, and c is our constant here. So you'll see that's the first thing I did is I wrote a is equal to 2, b is equal to 2, and c is negative 1. So you know your solutions for x are going to be negative b plus or minus the square root of b squared minus 4ac all over 2a. Well, plug the numbers in. Negative b, that's going to be negative 2 plus or minus the square root. B squared becomes 2 squared minus 4 times a, which is 2, times c, which is negative 1. All over 2a, 2 times 2. Now it's just simplifying that out. So this first step came from, all I did is I said, well, 2 squared is going to give me a 4, and then I will be saying negative 4 times 2 times negative 1. That's going to be a plus 8 in there, and then I'm dividing by 4. So that's where that top term came from. On the inside of the root, you'll want to combine your terms. 4 plus 8 is, of course, 12. And I'll certainly want you to reduce these down into simplest terms. You can say, well, that square root of 12, that's not good because it has perfect square factors. Absolutely. So you can say, well, the square root of 12 breaks down to the square root of 4 times the square root of 3. And I know that the square root of 4 is just 2. So I simplified that root of 12 as 2 on the root of 3. And then after I do that, I can see that, well, I could factor a 2, and I could have factored a negative 2 out of the numerator, but I just factored a 2 out of the numerator. And that gave me 2 times the group, negative 1 plus the root of 3, and then that 2 canceled with part of the 4 in the denominator to give me the streamlined, simplified answer of -1 plus or minus the root of 3 over 2. Now, I will always, always, always prefer the exact answer as opposed to a decimal approximation. So you could just leave your answer in that format. That'd be great. Now, it says we can find the solution for the quadratic equation in the form ax squared plus bx plus c equals 0 using this quadratic formula, as we have seen. But as a part of that formula, the b squared minus 4ac portion, that's actually the most important part. That part's called the discriminant. It's just the part that appears under the square root sign inside the quadratic formula. This discriminant, it's what's going to tell you what type of solutions that you have. Now, if that discriminant b squared plus 4ac, let me go back just real quick. If that discriminant, there we go, b squared, I said plus 4ac, how dare I, b squared minus 4ac, if that discriminant, that part inside there, if it's a positive number, all that's telling you is that there's going to be 2 real solutions. And I say 2 unequal real solutions, just means there'll be different numbers. If the discriminant is 0, there's going to be 1 real solution, and technically it's repeated because it's just going to be -b plus or minus 0 over 2a. And we're going to talk about that later on. The fact that it's going to be like what's called a double root just means it's going to touch at that point and either go up or touch at that point and go back down. It's not going to cross the x-axis. It would just touch the x-axis at that point. But for right now, you can just say if the discriminant's positive, there's going to be 2 real solutions. If the discriminant is 0, 1 real solution. If the discriminant is negative, there's no real solution. Square root of a negative number is going to give you imaginary solutions. Now, in order to see that in action, what if I just ask you to compute the discriminant of 3x squared minus 2x plus 5? I'm not asking you for the solutions. I'm just asking you for what type of solutions there would be. So you say, well, instead of using the whole quadratic formula, all I have to do is think of the b squared minus 4ac part. In this problem, b is a -2, so I'd say, well, I'm going to have -2 squared, and then minus 4 times a becomes minus 4 times 3 times c times 5. I'll get -2 squared is 4, and then 4 times 3 is 12. 12 times 5 is 60. I'll get 4 minus 60. Well, I'm getting a -56. I know that the square root of a negative number is undefined. That just means I will have no real solution. So because the discriminant is negative, this equation has no real solutions. Now, the favorite topic in this section for me is radical equations. And radical equations are not hard to work with, but unlike every other equation type we've talked about where I said, oh, you don't have to check your answers. You don't have to check your answers. You always can. But with radical equations, you must. This is the first equation that we have encountered where you could do everything correct algebraically and get answers that are not valid. Now, that could also happen with irrational equations, but the only time that that would be the case is if your answer is a restricted value. We could get answers here that you're going to get an answer, it's not restricted, but it's just not true. And you haven't done anything wrong algebraically. And it has to do with the steps required in order to get rid of the radicals in these problems. So a radical equation is an equation in which the variable occurs in a square root, a cube root, or any root. We solve radical equations of nth root by raising both sides of the equation to the nth power. Now, about the only time you're going to really have to worry about your solution is when that nth power on each side is an even number. That causes sign problems on each side that can lead to solutions that are not correct. If you're working a cube root or a fifth root or a seventh root, it's probably fine in those cases. You're not going to really have to worry about your answers. Now, If necessary, arrange terms so that one radical is isolated on one side of the equation. So you can't solve a radical equation if you have the radical along with other terms on that side. It's much better to get it all by itself. Isolate the radical. Raise both sides of the equation to whatever the index is. So if it's a cube root, you'll raise both sides to the third power. If it's a square root, you'll raise both sides to the second power. Solve the resulting equation. If the equation is still contain radicals, we'll repeat steps 1 and 2. So sometimes you might raise to a power and you still have a radical left inside. So you'd have to do it again and again and again. And that can make for a pretty frustrating problem sometimes. I don't think we're going to see any of those. I don't recall any in the homework that required that third step. Check all proposed solutions, and this is not a suggestion here. It's a mandatory statement. You must check the proposed solutions. So now, if I give you the equation x plus 3, all under the radical, and then plus 3 is equal to x, we're supposed to solve for x. First step, I said, isolate the radical on one side. So I have to get rid of that that plus 3 on the right by subtracting 3. I get the root of x plus 3 equals x minus 3 after I get the radical by itself. Now, I know that this is an understood second root. All square roots are the second root. So to get rid of that second root, I have to raise both sides to the second power. I square both sides. Now, the square and the square root are inverse operations. They just undo one another. So I'll have an x plus 3 left on the left-hand side. On the right-hand side, it's x plus 3 quantity squared. And please don't make the mistake in calling that just x squared plus 9. Anytime you square a binomial, you get a trinomial. If you have to write that out as x minus 3 times x minus 3 and FOIL it, please do so. We'll have x squared minus 3x for minus 6x, and then you'll have negative 3 times negative 3 for plus 9. So now I have this nice quadratic equation resulting. I have to go in and solve that quadratic. We know in order to solve a quadratic, probably the most preferable method, or one of the most preferable methods, would be by factoring. So I just said, well, I'm going to try to get a 0 on the left-hand side by subtracting x and subtracting 3 on both sides. If I subtract x on the right, I get a minus 7x. And if I subtract 3, the 9 becomes a 6. So now it becomes a factoring problem. Can I find factors of positive 6 that sum to get to negative 7? Yeah. Negative 6 times negative 1 is positive 6. Negative 6 plus negative 1 is negative 7. So I get x minus 6 times x minus 1 is equal to 0. I use the zero product property now, and I set each of these factors equal to 0. Well, if x minus 6 is equal to 0, I'll get x equals 6. If x minus 1 is equal to 0, then x is equal to positive 1. Now I need to check both of these solutions. Right now, I'm thinking, okay, they're both solutions, but since it's a radical equation, I'm guessing that one of them will be excluded. That's typically the case. Now, I go back and I check 6 in the original problem. If I do, I'll try to plug a 6 in. I'll get the square root of 6 plus 3, and then plus 3. Square root of 6 plus 3, it's the square root of 9. The square root of 9 is 3. 3 plus 3 is 6. And I'd have a 6 on the right-hand side as well. So, yeah, 6 equals 6. Check. I know that 6 is a solution. I check the other solution, or what I think the other solution is, the 1. So I'll plug a 1 in here, and I get, okay, the square root of 1 plus 3. That's going to give me the square root of 4. And then when I still have the square root of 4 plus 3 on the right-hand side, I have a 1. Well, now, please don't make the mistake here. I could see somebody thinking, well, hey, couldn't the square root of 4 be a 2 or a negative 2? No, it cannot. The square root of 4 is only 2. So I can say, well, that square root of 4 is 2. 2 plus 3, that's 5. 5 does not equal the 1 on the right-hand side, and it's because the square root is only possible to be a positive number that this is invalid. So you say, well, since the square root of 4 cannot equal a negative 2, this other side can never be true. That means 1 is an extraneous solution. It's a solution we arrive at through correct algebra. That is not a solution to the original problem. The only solution is our x equals 6. Gorgeous section here. That gives you a lot of different problems to look at. Please do try all of these throughout the homework assignment. Check against the book homework problems that I have worked in the section if you run into any troubles. And as always, ask me for any help if you should need it. I'll be glad to help.